All right, here we go. This is the Chapter 12 problem set. Let's jump right in. Question 1 says, the figure shows 3 situations in which the same horizontal rod is supported by a hinge on a wall and one end of the cord is at the other end. Without written calculation, rank the situations according to the magnitude of the force on the rod from the cord, the vertical force on the rod by the hinge, and the horizontal force on the rod by the hinge greatest first. So what I think is interesting about each of these situations, and I'll sketch them really fast here, is that like we have the wall, okay, and then we have the boom arm here. Okay, and it's supported by this hinge that's right here. Okay, now in each situation, regardless of whether the cord is straight up, up and out, or up and in, I think what's interesting is that the vertical has to be the same each time, because the forces on this, like the earth is pulling it down. Right, we got a little mg here, and so this cord, the vertical part of the cord force, has to balance out this force and this torque for that matter. And so A says the force of the cord so the force of the cord, you know, the vertical has to be the same, but this one here, I'm gonna call these 1, 2, and 3. So 1 not only has to pull up, but it has to pull up and in, and 3 has to pull up and out. And since you have the same angle there, I would say the force of cord on the rod, if I do greatest first, I would say that 1 equals 3 and then 2. Because 1 and 3 have to pull both horizontally and vertically, and since the angle is the same, they're going to pull the same, where 2 only has to pull up. B asks for the vertical force from the hinge. So what I think is interesting about this one is that if you look at 2, since 2 is only pulling straight up, the hinge actually doesn't have to supply any horizontal force at all. So that to me is really interesting. So when I think about the vertical force, since all strings are applying the same amount of vertical force themselves and the earth is pulling down here, I would actually say that the amount of vertical force from the hinge is 1 is equal to 2 is equal to 3. Because it only has to balance out with the same amount of vertical force from the cord and from the mg. C says, what about the horizontal force? In this case, 2 has no horizontal force at all because this cord is only pulling up, so the hinge doesn't have to make any left or right forces at all. And since we have the same kind of symmetry, this one pulls up and out, this one pulls up and in, and so what's funny is because this one pulls up and in, the hinge would have to push out. Since this one pulls up and out, the hinge would actually have to pull in. So I would say 1 is equal to 3 on this one, and then 2. But what's funny is 2 actually doesn't have to supply any horizontal force at all. Let's look at the next one. This one says, the figure shows 4 overhead views of a rotating uniform disc that are sliding across the floor. 3 forces, F, 2F, and 3F, act on each disc, either at the rim or at the center or halfway between the rim and the center. The force vectors rotate with the disk. These are just snapshots. Which disks are in equilibrium? What does equilibrium mean? That's the important thing. So equilibrium, what does that mean? Well, it has two contexts here. It means that the net force is equal to 0 and, it doesn't, it's net force, not net force X. It's net force is equal to 0 and the net torque is equal to 0. So let's look at these three. Let's look at A. When I look at A, it has 3F to the right and 3F to the left. So I'm noticing that the F net is equal to 0. Let's talk about the torques. 3 doesn't supply a torque. 2 supplies a torque. So it's 2F at half the radius, and this is 1F at twice the rate, or at the full radius. So I think the net torque here is equal to 0, and I'm going to say yes. That one's in equilibrium. Let's look at B. I'm noticing that all forces to the right, so I would say that the F net is greater than 0, so not in equilibrium. When I look at C, I got 2 F's to the right, I got 2 F's to the left. That looks good. And this is supplying a torque, making it rotate clockwise. This is supplying a torque, making it rotate counterclockwise. So I think that for this one, F net is equal to 0, and the net torque is equal to 0. So I'm going to say C is also in equilibrium. And what about D? I have 2 F's to the left and 2 F's to the right, so it looks like F net is equal to 0. But I have 2 F's supplying a torque, and I only have, oh gosh, that's supplying a torque in the same direction. So here, the net torque is much greater than 0, so not in equilibrium. So one's in equilibrium, A and C. All right, I love everything about this problem. So this is question 5. Actually, I don't want to say I like everything about this problem. I don't like the fact that all of the little penguins look the same size because they have different masses. Let's see what the problem says. It says, in the figure, it shows a mobile toy of penguins hanging from a ceiling. Each crossbar is horizontal, has negligible mass, and extends 3 times as far to the right of the wire supporting it as to the left. Penguin 1 has mass 48. What are the masses of penguin 2, 3, and 4? So the penguins have different masses, and the bars themselves don't have mass, so that's going to be important. So the way to approach this is to literally just sketch it up and see what happens. So I'll start up here. Okay, so this is the situation, and then it's hung from here up onto some kind of support up here. Okay, so it tells us one thing. It says, look, this one over here, 48. No problem. So instead of drawing the penguins, I'm going to draw little boxes. Now, I'm going to draw the boxes the same size, but the implication is that they can't have the same size or they wouldn't balance, right? So what I'm going to notice right away is that net torque is equal to 0. That's for the whole thing and for each individual bar. When you look closely, you're going to notice that this distance is 1 and this distance is 3. And what that means is that the torque for this has to balance. So that means that because it's 1/3 the distance, it has to be 3 times the weight. So if I call this bad boy over here, if I call this one, let's say this one weighs X. I should probably use W, but I'm going to use X. How much does this one weigh? This one has to weigh 3X. So now the torque's balanced on this bar. Okay, let's go to the next one. So since the bar itself doesn't have any mass or weight, what is pulling down on this string right here? Well, it's 4X. So if we just look at this bar, we have 4X down here. We have the same ratio. This is 3, this is 1. So since it's 1/3 the distance, it has to be 3 times the force. So this one has to weigh 12X. And so now, what's my total? I have 1 plus 3 plus 12. So on this string here is 16X. I have the same distance, 3 to 1, which means if this is 16X, this one over here has to be 3 times as big, which is 48X, which is cool because 48X equals 48. Therefore, X is equal to 1. So that means that this guy weighs 1, this guy weighs 3, and this guy weighs 12. I think that's such a cool problem. All right, let's look at this problem. This is a pretty classic physics type equilibrium problem. And we've done problems like this, but we haven't had like this weird angle. So part of this thing is going to be a geometry issue. All right, part of this is going to be a geometry issue. But let's talk about what this looks like. So I have this strut right here. Right, and let's put the stats on so that we can remember what it looks like. All right, so it says this is a concrete block of mass 225. So big mass is 225 kilograms. The strut here (45 kilograms). It says a couple things about the angles here. It says that the angle theta is equal to 45 degrees. And this angle here, we call this angle phi. It says it's equal to 30 degrees. And the first thing we want to know is what is the tension in the cable. So we're trying to solve for this T here. So because this is partially a geometry problem, we really have to get a sense of what's going on here. So we know it's a rigid object that's free to rotate. So let's draw it and see if we can't come up with some forces on it. So here's our strut here, okay? We know that this thing is pulling down with some large force, big mg. We know that the earth pulls it down from the middle. Little mg, okay? We know that there's a hinge down here. So the hinge has to push up at least, and this strut is pulling it to the left, so I think the hinge is probably pushing it to the right. So we're going to call this the hinge X, I'm going to call this one the hinge Y. And then there's a tension. And the tension's in this direction. Now, it's going to be important for us to realize that the tension here is pulling at some weird angle. And realizing what the angle is going to be the key to our success moving forward. So, we know the net torque is 0, so that's going to be important. So let's start with that as a statement. Net torque is equal to 0. What are the things that supply torques? So, start down here. Let's make our pivot point the hinge. Okay? Let's make our pivot point the hinge. I don't have a good color for that. Let's make it black. So we're going to make the pivot point the hinge. 1, it's natural to do so. 2, I don't know either of those forces, so we don't have to include them in our torque statement. So what's the first one? So halfway up here, we have L over 2, little mg, and this is the sine of what angle? Well, in this case, it's not theta, it's going to be 90 minus theta. Because if you notice, this is theta here, that's 90 minus theta, and you'll notice that if I put the force here, we would have the same angle there. Okay? Up at the top, we have at L, we have big mg, and again, it's at the angle sine 90 minus theta. And then I have one more. I have this tension here also acting at L. Now, this is the hardest part of the problem, is trying to figure out what angle that is. That angle is here, okay? It's this angle right here. All right? And it is not obvious what that angle is. All right? It's this angle that exists right here. And I'm going to call that angle alpha, just so that we have, it's not phi, it's not theta, I'm going to call it alpha. So, these are the torques on here. There's 3 torques, they balance. Let's figure which ones are positive, which ones are negative. Little mg would go this way, that seems to be negative. Big mg would also go the same way. And then T is what's balancing it out, so we'll call that one positive. So if I rewrite this, I end up with LT sine alpha is equal to L over 2 little mg sine 90 minus theta plus L big mg sine 90 minus theta. So if we can figure out what this alpha is here, we see that L's magically disappear. If we can figure out what this alpha is, we should be good to go. So let's come back up here and let's look and see if we can't do the geometry. So what I'm noticing here is that this angle right here is phi. We know that one's 30 degrees. This is 45 right here. So that means that the rest of it is 135. And then what am I left with here? Well, I know that the 3 angles in a triangle have to add up to 180. So I know that 180 has to be equal to 30 plus 135 plus alpha. And alpha is equal to 15 degrees. And so now I can put that in. So the L's magically disappear. So I have T sine 15 is equal to little mg is 45 times 10 over 2. sine, well, this is funny because theta is 45 degrees, so 90 minus 45 is 45. Plus big MG, 225 times 10 times the sine of, again, 90 minus 45 is 45. T equals, let me get my handy dandy calculator. I got T equals 6.762 newtons. Now, again, if you look at the textbook answer, it's going to differ slightly because of the fact that you're going to be using 9.8 instead of 10. In order to figure out the hinge force, we're going to have to do the F net in the X and the F net in the Y. Okay. If I do the F net in the X direction, I know it's equal to 0. Here, my F nets in the X direction are hinge X minus tension X. Now, the tension X is going to be here. And then you're going to have the tension Y here. So what's nice about this is we actually know this angle here. If I look up here at the strut, we can see that this angle here, phi, which is 30, is going to be the same as that one there. Those are alternate interior. And what that leaves me with is that Tx is equal to T cosine phi. So I can solve for Hx. Hx is equal to Tx, which is equal to T cosine phi. So I'm going to go 6.762 cosine 30. Handy dandy calculator. And I got 5.856 newtons. So that's the tension in the X, which is what they ask for. And then if I want to do F net in the Y direction, also equal to 0. So in the Y direction, I have hinge Y, up, minus little mg, minus big MG, and which way is the tension in the Y direction? Minus Ty. We're going to notice that Ty is equal to T sine phi. Oh, that was nice, Tom. Let's try that again. Much nicer. So the hinge in the Y direction is going to be little mg plus big MG plus T, we'll do T sine phi. So this is 45 plus 225 plus calculate that real quick. And I got 6081 newtons. And I think that's all I asked for. A lot of times they'll ask for what is the total force by the hinge, and you would have to use a Pythagorean theorem, but this is good enough for now. All right, let's move on to the next one here. Now, this next one, it's a little bit conceptually challenging. I'm going to blow this up because we're going to need a little bit of geometry. But what it's saying here is that we have a wheel here, and let me write a couple of these things down here. It says that the radius here is equal to, now it says 6 centimeters. We know that that's 0.06 meters. And then it's sitting, and we're going to try to pull it over this step here. The step here has height is equal to 3 centimeters, which is 0.03 meters. And we're looking for the F value here. Okay. It also says that the mass is equal to 0.8 kilograms of the wheel. So what force is going to allow it to come over here? Well, right now, here's our situation. If I were to draw a wheel over here, I'll use a little circle. It'll be easier that way. What are the forces? Well, we know that there's some mg here. We know it's sitting on the ground, and so there's some normal force here. We know we're pulling it to the right with some force F. And there's this, it's resting on this hinge, and so there's some weird hinge force, which ostensibly in itself would be a normal force also. Pushing that way, I'll call that, it's not a hinge, it's a corner. We'll call it the corner force. C for corner force. So we have all these forces on our wheel. And we want to get it so it rolls over this. Well, how do I know when I get it to roll, right? The question is, it's a tricky one because what is the, let's say it says applied horizontally at an axle of the wheel is necessary to raise the wheel over the step obstacle. So I want to get it to just go. So here's the necessary condition that is not obvious in the problem. So at the minimum force, okay, as it just starts to roll, two things are true. One, the net torque is still equal to 0. Because of the fact that it is just beginning to start to roll, okay? The net force is also still equal to 0, which is a weird thing. And this is the one that's important, but the normal force goes to 0. So think about that. I'm going to start pulling on it as it just starts to roll over this corner here. It loses contact with the ground, and that's the moment, is when it loses contact with the ground. That's when the normal force goes to 0. And that's what we're going to use in our understanding of the problem. So, let me start again. So if I go back and I do normal force is equal to 0, I still have my weight, mg. I still have my applied force, F. I drew him a little bit bigger here so that we can see him. And I still have my corner force. Pushing this way. And so I have these. What I'm going to do is I'm going to set up the net torque statement. And when I set up the net torque statement, I can see if I can't solve for these things. We have a couple issues here. One, we have to decide on a pivot point. I think the best pivot point to use is the corner right here for a couple reasons. One, I don't know how to solve for, and I'm not given the corner force. So if I put the pivot point there, it can't supply a torque. And also, we have a little bit of geometry here. So let's look at this. Now, one of the things we're going to need is an understanding of the inherent geometry to this problem. It says that the radius here is 6, which means that this radius is also 6. Does that make sense? So if I make this, I wonder if I can figure out what these angles are here. For example, if I look at this one here, make that 90 degrees, what angle is that? And if I know that angle, which we'll call theta, this one here is going to be 90 minus theta. How are we going to figure that out? Well, let's look at the geometry real fast. If I notice, I have this blue here, this yellow here, and then this green here. So I'm trying to match this triangle with this triangle. And let's see if we know any values. If you notice, this green one here is a radius. And here's the thing that's truly interesting, is it says the height here is 3. So if this height here is 3, and the whole radius is 6, what's my height here? It's also 3. So how are we going to find this angle theta? Well, it seems to me like this is the opposite side and this is the hypotenuse. So I can probably say the sine of my angle theta is equal to the ratio of 3 to 6. Sine of what angle is equal to a half? That's got to be 30 degrees. So that tells me that this angle here is 30, which means this one here must be 60. All right. So let's do the net torque then. First of all, net torque is equal to 0. So does the mg supply a torque? It absolutely does. If I go to draw that, here's my r vector. Here's my mg. So what distance is away? It's the distance of r. The force is mg. And the sine of, well, what angle is that one there? That's this one. So 90 minus theta. And then what else do I have here? At distance r, I have my f. And that's the sine of, this one is the theta. Those are, you're going to, one's positive, one's negative. Set them equal to each other here because they're both equal to 0. So I end up with r mg sine 90 minus theta is equal to r f sine theta. And we're actually solving for f. R's magically disappear, and I end up with mg sine 90 minus theta, all divided by sine theta. My m is 0.8, 10 sine and I got F is equal to 13.6 newtons. All right, let's look at this next one. All right, this last one is very similar to the latter problem. We're going to have another geometry issue, which we kind of have to work out a little bit. But let's write down what's given to us in the problem first. So it says we have this uniform plank with length L of 6.1 meters. All right, so let's write that down. So the total length is 6.1 meters. And it tells us it weighs 445 newtons. So the mg, its weight, is 445 newtons. Okay, I like that. Rests on the ground against a frictionless roller. So there's no friction with the roller. That's going to be important. Now, it says this little h here is 3.05 meters. Okay? And it says the plank remains in equilibrium for any value of theta that's greater than equal to 70, but slips if it's less than 70. So we're going to go ahead and say that our angle is equal to 70, because I know that if it were less than that, the whole thing would slip. Okay? So we're going to use 70 degrees as our angle. And what we're going to do is we're going to try to figure out the coefficient of static friction with the ground. This is what we're trying to find. Okay? Now we have a context for the problem. Let's start with a nice force diagram. All right, so what are the forces? Well, we know we're going to have an mg. That's the weight. Is that cool? And it's resting on the floor, so it's not slipping, so there's some frictional force this way. It's resting on the floor, so there's going to be some normal force this way. Cool. Now notice the top end isn't resting on anything, but it is here, it's resting on this roller. And so the roller is going to push it basically in this direction. Now, I don't know if it's perfectly perpendicular, but we're going to draw the roller force this way. Now, the thing is, you'll even notice from here, given the context of the problem, we're actually going to have to figure out what this length is here. But the force from the roller is here. And you'll see what distance it is. So this is F, R, for force from the roller. Okay. The angle here is also going to matter in a moment. Actually, I'm going to make it a little longer. So that's the force from the roller. Okay? So the thing balances, so what's that tell us about our net torque then? Net torque has got to be equal to 0. And so let's see if we can't find out what the torques are. So our pivot point, like we like to do, we'll make our pivot point down here. So what supplies a torque? Well, I know that mg, it's halfway, it's at the center, so it's halfway up. So L over 2 times mg times the sine of, well, if we're going to call this theta, then the angle it makes is going to be 90 minus theta. And what about the roller here? So we're going to say the roller's up here at a distance d. So when we think about the problem, you know the roller is at a distance d. which we're going to have to figure out what that is, times the force by the roller. Now, inherent in the problem is what we're going to say is the roller can only push perpendicularly. I don't know that that's implied in the problem or it's not implied in the problem, but we're going to go with this. We're going to go with this being our understanding, and we're going to see if that makes the problem doable in a way that we want it to be doable. So it's RF, and if it's perpendicular, what's going to be sine 90. If the weight were the only force, it would go this way, so this one's negative. If this were the only torque, it would go this way, so this one's positive. And so I end up with a problem that looks like this, where I have the distance to the roller force times the roller force, sine of 90 is 1, is equal to L over 2 mg times the sine of 90 minus theta. So I think we're going to have to do a little bit of geometry here to try to find out what the d value is. So let's talk about this triangle here. So I know that this is our distance d. This is the roller up here. This is the distance along the floor to the base of whatever, is this a rod or whatever? So this is d, that's the distance to the roller. This is h. Now, luckily h is given to us. So if I want to find my d value, this is the opposite side, this is the hypotenuse. And so the sine of my angle should be the ratio of the h to the d, opposite to the hypotenuse. Therefore, d is going to be h divided by the sine of theta. And luckily, we know both of these, 3.05. We're using 70. Handy dandy calculator. So I got my d value to be 3.25 meters. Now the whole plank is 6.1, so 3.25 is a little bit farther along the plank than halfway. So it looks like I drew it. Okay. So let's see if we can't plug this in now and go for it. So I have 3.25 times the force by the roller is equal to L, 6.1 divided by 2, times mg, which is 445, times the sine of 90 minus 70. Okay? Let's get a little handy dandy calculator out. And I got the force from the roller to be equal to 143 newtons. Now, that's just the force by the roller. That doesn't actually answer my question. We still are trying to find the coefficient of friction, which means we need the normal force and the frictional force. But I think if we do net force in the x and net force in the y, we might be able to make it happen here. So let's try that. One thing I want to notice here is that because the roller is a force up and to the left, this is the roller force in the y direction, and this is the roller force in the x direction. And we'll see how those match up here in a second. So if I want to do the net force in the x direction, I know it's equal to 0, and it's equal to the frictional force minus the roller force in the x direction. That's that one right there. Therefore, my frictional force should be equal to my roller force in the x direction. And if I look at this, depending on the angle you use here, what we're going to notice is that that little angle there, so this one is theta, this one is theta, so that one there is 90 minus theta. So this is going to be equal to the roller force times the cosine of 90 minus theta. Let's calculate that real quick. Got 134 newtons for that one. All right, and let's do the F net in the y direction. It's equal to 0. So we got 3. We got a normal force, which is what we're going to solve for. Okay. Minus the weight. But plus the F in the y direction, the roller force in the y direction. So therefore, if I want to solve for my normal force, it's going to be equal to the weight minus the roller force in the y direction. And the roller force in the y direction well, it's the roller force, and you can see it would also be this component right here. So we're going to say sine 90 minus theta. The weight is 445 minus 143 sine 20. Calculate that. I got 396. Okay? And now the moment of truth. We know that our coefficient of friction is the ratio of the frictional force to the normal force. In this case, the frictional force is 134. The normal force is 396. And I got 0.34. And there's no units. It's technically newtons per newton, but we're going to let them cancel. All right, that's the problem set.